So yesterday, I guess we sort of just recapped about factorising polynomials and with complex numbers. This thing we're going to look at now about multiple roots is a new idea. And here's the theorem. If we have a multiple root, so the polynomial has a root of multiplicity, let's call it m, then what will happen is the derivative will have a root of multiplicity 1 less. So if it has a root of multiplicity m, we know it can factorise to be x minus a to the power of m times some other polynomial where a is not a solution to that other polynomial, because that would change the multiplicity of it. Alright, let's differentiate. So we use our product rule, write down the first, diff the second, plus write down the second, diff the first. But in order to differentiate the first, we've got to use our chain rule, bring down the power, lower the power, m minus 1, diff the inside. That, you'll notice, has a common factor of x minus a to the m minus 1. And that's basically what we're trying to prove. Because what we're saying is, if the original polynomial has a root of multiplicity m, so there'll be a factor of x minus a to the power of m, then the derivative will have a factor of x minus a to the m minus 1, which we've just proven, because in that second brackets there, whilst I don't know what qx and q dash x is, I know they're polynomials. So it is going to be x minus a to the power of m minus 1 times some polynomial. I know a is not a solution to rx, because when I substitute in, I won't get 0. The first part will be 0, a minus a, but then it's plus m times qx, and remember we defined a as not a solution to qx, so we know that that's not going to have another root. So there's our proof. Well, let's go and use it. So we've got this cubic, but it's told us it's got a double root. Now the advantage of that is, it is a lot easier to find roots of quadratics than it is cubics. Because a quadratic, we know, oh yeah, what multiplies together to give, and that sort of idea. So if I've got a cubic and I know it's got a double root, so there's our polynomial, the derivative will be a quadratic. And I know that one of these roots of the quadratic will be the double root of the cubic. So if I factorise the quadratic, I get two possibilities: minus a third or 3. Now, when I look at my original polynomial that I'm playing with, logically it would be the 3. Because if it was the minus 1/3, then I would see a factor of 3x minus 1. Well, the original polynomial is monic, so it's not going to have a factor of 3x minus something. So logically it's going to be 3. It is still a good idea to check, of course. So if you substitute in, we get 3 cubed, which is very good, minus 4 times 3 squared. 3 squared is 9. 9 fours are 36. So 27 minus 36 is? Okay. Minus 3 times 3, so minus another 9. Plus 18. Voila. So it is a root of the original one as well. Okay. So we know x minus 3 is the double roots. It then becomes easy to factorise my cubic, because there's only one other solution to go, and I know, well, constant times the constant will equal the constant. So minus 3 squared is 9. 9 times 2 is 18. So x plus 2 must be the other factor. Haven't answered the question yet, because the question said solve the equation. So solve the equation, we get negative 2 or positive 3. Here's a nice one, 1991. What's really cool about this one is it's on a couple of niceness. Niceness, is that a word? But you'll notice the year, 1991, which of course is palindromic. And you look at the coefficients of our polynomial, and it goes 1a, b, a1, which is also palindromic. So nice little... Now, I don't know whether they intended that or not, but I thought that was kind of neat. But where 2 plus b squared is not equal to 4a squared. And you're probably looking at that and thinking, well, of course. Fancy even suggesting that 2b squared could equal 4a squared. We'll find out in a second why that's important. First part of the question. Show that alpha, so alpha is the solution, cannot be 0, 1 or minus 1. Well, I guess the easiest way is using the factor theorem. If I sub in 0, I get an answer of 1. So no, alpha can't equal 0. If I sub in 1, I get 2a plus b plus 2. I'm not sure whether that can be 0 or not yet. Well, if I sub in minus 1, I get minus 2a plus b plus 2. Hang on, that's where this becomes useful. 2 plus b squared cannot equal 4a squared. In other words, 2 plus b cannot equal plus or minus 2a. So therefore, b plus 2 cannot equal minus 2a, so polynomial 1 can't equal 0. And in the other one, b plus 2 cannot equal positive 2a, so polynomial negative 1 cannot equal 0. That's why that extra piece of information was important. So we can now say that, well, plus or minus 2a plus b plus 2 can't equal 0. So polynomial 1 can't equal 0. Polynomial negative 1 can't equal 0 as well. So alpha can't be 0, 1 or negative 1. Okay. We now have to show that the reciprocal alpha is also a solution. So we know alpha is a solution. We want to show that the reciprocal is also a solution. Right, again, let's use the factor theorem. Sub in 1 on alpha. We've got to show that this is equal to 0. Well, it's an algebraic fraction, so let's make it all over the alpha to the power 4 and have a look what happens on the top. We get 1 plus a alpha plus b alpha squared plus a alpha cubed plus alpha to the power 4. That was the beauty of the symmetry of the coefficients, because hopefully you recognise the top there. That actually is polynomial alpha. And we know polynomial alpha is equal to 0, because alpha is a root. So therefore, 1 on alpha also equals 0. So alpha, if alpha is a root, 1 on alpha is also going to be a root. So when we're finding solutions, as soon as we've got one solution, we've got 2 straight away, because we know its reciprocal will be there as well. Deduce that if alpha is a multiple root, then its multiplicity has to be 2, and 4b is equal to 8 plus a squared. Okay. Remember, we just proved that whenever we get a solution, we get 2 solutions. Because as soon as we find alpha, we get 1 on alpha. But they're now telling us alpha is a multiple root. So if it was a double root, 1 on alpha must be a double root as well. Because I've got 2 roots of alpha. As soon as I got those 2, I must get 1 on alpha for each of them as well. Right? Because we just proved before that if alpha is a root, 1 on alpha is a root. So if I've now got 2 roots and they're both alpha, then I must have another 2 roots that are 1 on alpha. So that's 4 of the roots. But we're dealing with a quartic. So we know there can be no more than 4 roots. So that's all of them. The roots are alpha, alpha, 1 on alpha, and 1 on alpha. So that is the first part of our question. If it is a multiple root, so we're saying, okay, if it's a double root, its multiplicity is 2. Can't be any more, because it'll create too many roots. So we've got a maximum of 4 for a quartic. So no roots can have a multiplicity of greater than 2. Now the other part of the question. We now need to deduce that 4b is equal to 8 plus a squared. Alright. Here's our derivative. Remember, I now know it's a multiple root. So if it's a solution of the function, it's a solution of the derivative as well. So let's work out the derivative. 4x cubed plus 3ax squared plus 2bx plus a. I know that alpha and 1 on alpha, for that matter, are solutions to this, because it's a double root. So if it's a double root of the polynomial, it's a single root of the derivative. So I know one root is alpha. I know another root is 1 on alpha. There is a third root that I don't know to this cubic. Let's just call it beta. It'll be a solution to this cubic, but it won't be a solution to the original polynomial. It's not one of the double roots. Okay, sum of the roots 1 at a time, and I get minus 3/4 a. Sum of the roots 2 at a time, and I get a half b. and product of the roots, or sum of the roots 3 at a time, I get minus a quarter a. But I now know that that third solution to the derivative is minus a quarter a. Okay. Well, I can sub that in for beta. So if I sub it into beta into the first one, I now have alpha plus 1 on alpha minus a quarter a is equal to minus 3/4 a. Move the a over. I've got alpha plus 1 on alpha is minus a half a. Okay. If I substitute it into the second one, so I end up with 1 minus a quarter a alpha minus a quarter a 1 on alpha, and that's going to equal a half b. I've factorised the minus a quarter a outside of the alpha plus 1 on alpha, and the reason I've done that is because over here we worked out what alpha plus 1 on alpha is. So I can substitute that in for alpha plus 1 on alpha, rearrange it, I've got the result that they want. 8 plus a squared is 4b. I'm sure there's other ways of doing that, but there's one way of coming up with the result. Okay, so in our Cambridge 5B, we'll do one of 16, and then in Patel we've got some questions as well. Oh, in Patel as well, all right.